GT 2212 Lab 3 Magnetic Field of a Bar Magnet. Introduction, the purpose, and the fundamentals. So the purpose is to observe and understand magnetic fields and how they're affected by distance, as well as using the Biot-Savart law to find the bar magnet's magnetic moment. Learning that the Biot-Savart law and distance dependence can be applied to bar magnets to get accurate results. The Biot-Savart law is seen right there. And then another fundamental is creating a computational model to help visualize magnetic field in a 3D space, understanding bar magnets, superposition, linearization, and then there's other relevant formulas. Introduction. So the system is the bar magnet, that gray rectangle, and the surroundings are everything else. And the task was to find the location of the magnetometer, that red X on the phone. And that was found by sliding the phone perpendicular to the ruler and placing tape to mark when the magnitude of the bar magnet is at its highest. And then you can use those two pieces of tape to find the X. The experimental data sheet. This is using the values for distance from the bar magnet to the magnetometer were linearized, meaning that you take ln of each side and then graph to the right. And then all of these values were just recorded in the table. Observations: when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, and the phone's orientation has a great effect on the data. It had to also move other electronic devices. I also had to move other electronic devices farther away from the phone and the magnet because they were affecting my data as well. Calculations. The distance dependence equation is y equals right there, and that was found on our graph. And then taking the slope, and you can find k, and then using Biot-Savart law, set it equal to distance dependence, and you can solve for the equation in red, and I got my value of mu being 0.002153 Newton meters per Tesla. Glow script. 1, create a cylinder to represent the bar magnet at the origin and plugged in my mu value. And then 2, I created a function that defines magnetic field at any point to the bar magnet at the origin. And 3, I created 6 observation locations, 2 on axis and then 4 perpendicular. And then 4, created arrows to represent magnetic field at each observation location. And then here, I created a magnetic field 45 degrees off the axis using the measured dperp from earlier in the lab. And then I drew an arrow to represent the magnetic field 45 degrees off the axis. Here's the results of the lab, showing the showing the values given from the code, and the direction of the arrows. The theoretical off-axis field is 2.28 times 10 to the negative 8, and then the experimental off-axis field is 4.7 times 10 to the negative 5. And there was a big error in my code. I'm not really sure how it happened. Either calculation or just how it was measured was incorrect. Sources of error: the position of the magnetometer was not found precisely, and the system was not isolated. I did this in a computer lab, but there were a lot of computers nearby. I tried to isolate it as best I could, but clearly that did not work. Additional questions and conclusions. What if you hadn't oriented your experiment to compensate for magnetic north and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The Earth's magnetic field would have interfered with the data, and it would have been accounted for when taking it. It would have to be accounted for when taking the data. If it wasn't, then it would have altered the results. What if you were to stick 2 identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The measurements would roughly double, and the direction of the magnetic field would be the same.